Hello again. This is Math 2245 coming to you from the College of DuPage, and the title of this lecture is Matrices Part II. As always, please be attentive listeners as you watch this video. In the last video, we concluded with the result that matrix multiplication is not commutative, and that's an important thing to remember. And we here continue our discussion of matrix multiplication. So for the sake of completeness, if A is a n by p matrix, n rows and p columns, and B is a p by m matrix, p rows and m columns, then the entry in the ith row and jth column of AB is given by the formula. The ijth interest in the product is, and this is the sum. And notice that we're summing on p, so we get 1, 1 here, 2, 2 here, 3, 3 here. So it is AI1 B1J plus AI2 B2J plus AI3 B3J plus, and so on and so forth, plus AIP BP. Now this formula is useful on occasion, but what you're going to find is it's used mostly in proofs and computer programs, or perhaps when you compute one. But this is certainly a valid formula for computing the product of matrices. On occasion, it's also going to be convenient to know a single row or a single column from the product and not just the whole product itself. And this following theorem tells us how to get our hands on that. So this theorem says, assume that A and B are appropriately sized so that AB is defined. Then the ith row of AB is given by the matrix product. You take the ith row of A times the matrix B. And the jth column of AB is given by A times the jth column of B. That proof follows just from calculation and listing things. But we're going to use that theorem to compute the second row and third column of A times C for the following matrices. And realize that this is defined because this is 2 rows, 4 columns. This is 4 columns, 3 rows. So the product is going to be a 2 by 2 by 3. Okay, so these are matrices from a previous example, and so let's just find the second row first. So according to the fact from the theorem, this means we need to multiply the second row of A by C. So let's look at that work. So here's the second row being multiplied by this. Now what you do is you stand this up and you multiply, and you see that what you do get is minus 56, minus 23, and 81. And sure enough, if you compare that with our previous example, this is the correct second row of the product AC. Now let's use the fact to get the third column. That means we need to multiply A, here you see A, by the third column of B. And we get that this is going to be 1781, and again, this gives us the correct answer. These are nice little quiz or exam problems because you do not have to do the whole matrix in order to answer such a question. Now, we can use this fact about how to get individual rows or columns of a product, as well as the idea of partition matrices that we saw in the previous section, to derive a couple of new ways to find the product of two matrices. So suppose we've got matrices here in P and PM in terms of dimensions, and so the product is defined. And so if we're talking about considering the partition of the matrix, so A looking like this we could take vectors representing just the rows and call this row 1, row 2, and so on through row m. And so what we have is A times B is just this row matrix times this partitioned row matrix times B, and that's the same in this theorem that we just talked about as R1 times B, R2 times B, and Rn times B. A second way of doing this is if you partition B with the columns, and I'm calling these C1 is the first column, C2 is the second column, Cm is the third column, then we can use our theorem again, the fact that the jth column of AB is given by A, the matrix, times the jth column of B, and so the product AB can be written as a partitioned matrix as follows. So this is A times each of those columns, and then this is what we get. So you see this gives us several ways of computing a product of matrices. And so in example 8, we're going to take A and C, and we'll calculate A times C, and we'll use both of the new methods. So first, what we're going to do is use the row matrices of A, and there's two of them. There's R1 and there's R2. So the rows of the product are, this is going to be row 1 times that, and row 2 times this. And so what we're going to get is that these are the rows for the product. So if we put these two things together, we find that AC is, and these are the rows that we found through our calculation, and this is the correct answer. Now, we were supposed to do it another way as well. And so let's do it using the columns. Now, these are the columns that we have. And so A times C1 is going to be, and you can see how to do it here, is going to be 1356 minus 56. A times the second column is going to be this, and A times the third column is going to be this. So if we put it all together, you see that we get the correct answer yet again. So these are additional ways to compute the product of two matrices. And we can also write matrix product as a linear combination of the column matrix. For example, suppose that you have A times X. Now here X is this vector, and so we just do the matrix multiplication, and we get this as our solution. This is an n by 1 matrix when I take A, which is n by P times a P by 1, and so I get this as my n by 1 matrix. But if we break that up using matrix addition, we can say, oh, this answer is really the summation of those, and that is the same thing as taking x1 times this first column vector plus x2 times this second column plus xp times the third. So you see that this is a linear combination of the column vectors. And so we can have that AX also can be represented as a linear combination of the column vectors. Sometimes this representation will be useful. And in fact, let's do that. We'll compute AX directly and as a linear combination for the following system. And so this is what we get for A times X, and here is the linear combination method of computing that product. So you see I'm taking 2 times the first column, minus 1 times the second column, 6 times the third column, and 8 times the fourth column. And then I do these scalar multiplications, add them together, and I get the same answer. Now, a notation that we will often use, suppose I'm looking at the system of linear equations. And here you have n equations in m unknowns. These are the right-hand side constants. But instead of thinking of these as a set of equations as we did earlier, we could think about this side as a vector of size n minus 1, or n by 1 matrix. So this is b1 through bn. And here I have the same thing. But if I break this into using factoring and the definition of matrix multiplication, this is the coefficient matrix times a vector of unknowns, x1 through xm, equal to this. So if we denote the coefficient matrix by A, and the column matrix containing the unknowns by X, and the column matrix containing the B's by B, again these are bolded so they're vectors, we can write the system in the following matrix form. This is AX equal B. Now, in many of the sections that follow, we'll write general systems of equations as AX equal B, just because this is a very compact and clear way to write them. Okay. We're now ready to define a new concept. So this is the definition of the transpose of a matrix. So if A is an if A is an N by M matrix, then the transpose of A, and the way we write this is A with a superscript of T. And the superscript looks like an exponent, but this is an M by N matrix. And notice that A was an N by M, so this is basically switching the rows and columns, and this is the matrix that is obtained by interchanging the rows and columns of A. So the first row of the transpose is the first column of A, the second row of the transpose is the second column of A, and so on. Likewise, the first column of A transpose is the first row of A, and the second column of A transpose is the second row of A, and so on. Now, sometimes you'll see it defined this way. So A is Aij, and notice I'm making note of the fact that this is an N by M matrix. So the transpose is, notice that these are reversed, so this is Aj, where I and J were what was defined here, and this is now the dimension here is M by N for all Ij. Now notice the difference in subscripts. So under this definition, the entry in the ith row and jth column of A will be in the jth row and ith column of A transpose. Notice that these two definitions are really the same definition, but they don't necessarily look like the same thing at first glance. We also are going to define something else that will come up in equations and theorems and proofs, and this is called the trace of a matrix A. Now, for the trace to be defined, you do need a square matrix. So this is of size n by n. So the trace of A, and usually this is denoted TR, the first two letters of trace of A, is the sum of the entries on the main diagonal, or the trace of A is A11 plus A22 plus all the way down to ANN. And again, if A is not square, then the trace is not defined. So let's practice that just a little bit. So let's start with A, B, C, D, and E. Okay, so if we take the transpose of A, what will happen is that we will write A, instead of being a 2 by 4, it's a 4 by 2. The first row is the first column, and the second row is the second column. Now the trace of A is not defined because A wasn't a square matrix. Now B is a square matrix. It's 3 by 3, but again you see that here I have 3, 2, minus 6, and 3, 2, minus 6 is the first column, and so on. So this is the transpose of A, and there is a trace of B. Now it's the trace of B, so it's the sum of the diagonal elements. So I say 3, 1, and 12, which is equal to 16. Now, if you have a vector, the transpose of a column vector is a row vector, but the trace isn't defined because it is not squared. Now D is a single entry in a matrix. It's a 1 by 1. It is square, but the diagonal just sums to 15. And here the transpose is going to actually be equal to the matrix that we started with. And E is again a square matrix. It is a 2 by 2. So minus 12 minus 7 is going to be the first column, and minus 7 10 is going to be the second column, and the trace is going to be these numbers added together as integers, and I get minus 2. Now notice that in the previous example, the transpose of D and the transpose of E were actually the very same matrices. So the transpose in each case was equal to the original matrix. These such matrices are called symmetric. This is a definition. So some things are symmetric and some are not. Now, there are many properties that are true about matrices, and we did talk about earlier that matrix multiplication was not commutative, but matrix addition is. Matrix addition is also associative, and matrix multiplication is associative too. Notice the groupings are different, but the order didn't change. Now, we do have to make statements about two distributive laws because matrices are not commutative. So if I have A times B plus or minus C, the A can distribute this way on the left. Similarly, if we have B plus C in parentheses as matrices times A, the A will distribute, but the A is always on the right in this case. And this is making note of the fact, and is because of the fact that matrix multiplication is not commutative. We have distributive properties that work with scalar multiplication. And here's actually three of those. And there also is an interaction this way with scalar multiplication. The proofs of these aren't hard, and sometimes we will use those. So it is important that you make note of these and think through them. And I think we really already talked about most of this. Now, we need to look at a couple of other ideas from real number arithmetic and see that they do have equivalent ideas in matrix arithmetic. So let's start with the fact that for real numbers, we know if I take 1 times a real number, that's the same thing as the real number times 1 is the number. So 5 times 1 is the same thing as 1 times 5, and that's equal to 5. So there is something that we can multiply a number by a number 1 that doesn't change the number. This is called the multiplicative identity when you studied your algebra. So we will have something that is playing the role of the identity matrix that will give the same result in matrix multiplication. So that is saying if A is an n by m matrix, then we have there is a matrix that I can multiply on the left by A. Now notice that this has to be a square matrix and is identity matrix with 1 along the diagonals, but it is a square matrix that's n by n. Now on the other side, what we have is this could be A times, but this would have to be, given the size we talked about for A, this has to be a square matrix with rows and columns of dimension m. But in either way, we'll get A. Now note that we really do need different identity matrices on each side, and that depends on the size of A. Now here's some examples that you may want to think about to give you some ideas with this. So here we have a 4 by 2 matrix. So that means if we take the identity matrix, which is 4 by 4, and this is just the 1 down the diagonals and 0 everywhere else, times A, and this matrix is defined because I have 4 columns and I have 4 rows. I get the matrix I started out with, A. Now, if I'm doing it on the other side, here, I need a 2 by 2 because this, the number of columns here is 2, so the number of rows has to be here. But if I multiply A times I2, I get A again. Now, just like the identity matrix takes the place of the number 1 in matrix multiplication, there's a 0 matrix denoted 0 for a general matrix and 0 for a column row matrix. And this is a little bit confusing. This is not a scalar. This is a 0 matrix. This takes the place of number 0 in most of the matrix arithmetic. And so we did say most. There are a couple of properties involving 0 in real numbers that are not necessarily valid in matrix arithmetic. So please stay tuned and be very mindful of those. But here are properties that we have. So if we subtract a matrix from itself, we get the 0 matrix. If we add 0 to a matrix, and it could be commutative, you'll get A back again. If you take 0 minus A, you get the negative of matrix A. And the 0 matrix times A is equal to 0. And A times 0 is equal to 0, and the scalar 0 times A also will give you the 0 matrix. But now, in real number arithmetic, we know if we have A times B equal A times C, and A does not equal 0, we must have B equals C. Sometimes this is a cancellation law, and you would say, oh, I'll just divide both sides by A. We also know in real numbers that if A times B equals 0, then we have to have A equals 0 or B equals 0. Sometimes this is called the zero factor property. Please note, this is very important, neither of these properties of real numbers are valid in general for matrix arithmetic. You might in fact want to come up with examples of those where matrix A times B is equal to matrix A times C, but the two matrices, matrix B and C, are not equal. And similarly, you might want to find matrices A and B such that you can multiply them together and have it equal to the 0 matrix, but neither of these matrices is 0. And in case you didn't do that, here are some examples of the results that we were just talking about. So if I take A to be this 2 by 2, B to be this 2 by 2, and C to be this 2 by 2, A times B is going to be 9 minus 10, 18 minus 20. And A times C is also going to be the same matrix. So you see AB is equal to AC, but this matrix B does not equal this matrix C. So you see you can't cancel the A. So at least in this case it doesn't hold, which means it doesn't hold in general. Now there are times when the cancellation law will be valid, but other times it's not generally valid, so you must be careful about that. And so, and we'll see that in the next section when we talk about inverse of matrices. Here's an example where we can take matrix A times matrix B. You should do that calculation, but you get the 0 matrix. So you see A times B is equal to 0, but neither of these factors are equal to 0. So you see there are some properties of real numbers that don't carry on into matrices and others that do. So you need to be careful. And again, this will sometimes be true, but it really depends, and we'll talk more about that later in future sections. Okay, so we need to be careful. Now, the next topic that we need to look at is, well, we can take powers of matrices. And we'll just work with positive exponents to start with, and then we'll define negative exponents in a bit. And so we start out with the following definition. So A to the a matrix A, which is a square matrix, we have to make sure that you can multiply a matrix times itself. That will mean it's going to be square. So if you take matrix A to the 0 power, that's going to be the identity matrix. And the size of the identity matrix is going to be the same as the size of A. And if we take then, so that tells us what we do if we use 0 as an exponent. If we take n being bigger than 0, and again an integer, we're going to say that A to the nth power is just multiplying the matrix A times itself n times. And we do have several of the standard integer exponent properties when we're working with matrices are true. So for example, and you should think about how would you prove this? If A is a square matrix and m and n are integers, and again these are positive integers so far, then A to the n times A to the m equal A to the n plus m. And A to the n whole raised to the m is A to the n times m. And you should think about why these are true and in fact be able to describe a proof. But this means, since we've defined scalar multiplication and exponents, we can also talk about plugging matrices into polynomials, and here is a definition for that. So if the polynomial p of x is an xn plus an minus 1 plus times xn minus 1 plus all the way down to a1 times x plus a0, we can take the same polynomial with the same coefficients and powers and plug in and talk about the polynomial p of the matrix A, and we just make this substitution. Notice that we are using scalar multiplication. Notice that the A0 is A0 times the identity matrix. Okay, so let's do a little bit of practice with this. I'm encouraging you to pause the video and actually verify these computations. But we'll start with a 2 by 2 matrix and talk about A squared, A cubed, and P of A, where this is P of X equal minus X cubed plus 10X minus 9. So in part A, we just take A times itself. For practice, you should do this calculation, and we get this as our answer. Now A cubed is the same thing as A squared times A, so I can take my answer from up here and just multiply by A again, and I get this number. So that is what A cubed is. And now we know what A cubed is, and we know what A squared is, and we know what A is. So we're pretty easy. It's not difficult, let me say it that way, to do this polynomial. So we plug in the values that we have, and notice that it's 9 times the identity matrix. We do the calculations, and we get this as our answer. Again, you should verify these calculations. Make sure that you understand them. Now, there are some properties of the transpose of a matrix that are important to understand. And you should be familiar with these results and, in fact, have a good idea as to how to prove them. We will prove some of them. So these are properties of the transpose. If you take the transpose of the transpose, so here you switch rows and columns, and you switch rows and columns again, you get back to where you start. If I take the transpose of the sum or difference of two matrices, that's the same thing as the sum or differences of the matrices. If I take the transpose of the scalar multiplication, C times A, that really is just C, scalar multiplication C times the transpose. And then if I take the transpose of the product A times B, I get the transpose of B times the transpose of A. Now, 1 through 3 are pretty easy. You should think about it. But let's go through the proof of property 4. Okay, and all we need to show is that the ith, jth entries are the same. So we know the entry in the ith row and jth column of AB is given by this product and sum. Now, if we interchange the ith row and jth column, of AB transpose, what we really done is the ith jth thing here is the jth ith version of the product, which is this. So let's suppose and denote the entries of A transpose and B transpose as A bar Aij and B bar Ij respectively. Often in linear algebra, figuring out a way to describe things notationally is part of the challenge. So based on the definition of transpose, we know that A transpose is A bar Ij, which is A Ji, and B transpose is B bar Ij, which is B Ji. So what we're going to show is that that these elements are going to be the same when I do that product. So let's look and see what we get. So we see that this and this, by definition, so the entry in the ith row and jth column of B transpose times A transpose is given by this product and sum. But if we plug in what A Ij bar and B Ij bar are, we get this for the ith jth elements, which is equal to this, and which is the same as this, which is what we had as the ith jth element. So what have we done? Well, we've managed to show that the entry in the ith row and jth column of AB transpose is equal to the entry in the ith and jth column of B transpose A transpose. Therefore, each of the entries are equal, and so that means that the matrices must be equal. Please check and make sure that you understand this proof. And note that our property 4, really we could do this in more generality. So A times B times C, the transpose of all that is the product of the transposes in the reverse order. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and take care of each other. We're all in this together. God bless you all.